Hi guys, this is lesson 7.6, exponential functions. You should already have in your notes the key concept from page 453. If you don't, go ahead and do that now. What you're looking at is that y equals a times b to the x. We'll look at an easier version of this later, just like we do with any formula. But the things that you need to know about this are when you're looking for an exponential function just from the rule or the equation like this, you're looking for x to be the exponent rather than one of the lowercase variables. So if x is the exponent, that's the first thing you're looking for in an exponential function. But there are some qualifiers here you need to think about as well. A can't equal 0, and the reason is if a equaled 0, what would happen to b to the x when we multiplied it? It would go away and we would just end up with y equals 0, which is not exponential. The exponent would be gone. The other thing to note is that b has to be positive. So b is greater than 0. A can be negative, but b cannot. And b cannot equal 1. And the reason b can't equal 1, if you think about it, no matter what power that exponent was, it wouldn't matter if b was 1, that exponent would no longer matter. Because no matter what power you put 1 to, you're always going to end up with 1. And then it would no longer be an exponential function because the exponent would be gone. Alright, and lastly, it says that x is a real number. That is part of the definition, although it might not mean as much to you at Algebra 1 because we don't use imaginary numbers yet. We will be learning about those in Algebra 2. So x must be a real number, but don't worry, in your Algebra 1 textbook, x will always be real. Problem 1 asks us to look at two examples and say whether the table or rule represents a linear function or an exponential function, and then to say why. Problem A gives us a table. I want to write that table vertically. We're used to using vertical tables instead of horizontal tables. They are a little bit easier to use in this type of situation, so I'm just going to rewrite the table vertically. And you may remember when we used these before, when we were learning about linear functions, the way we identified a linear function is we would look at what had to be added each time in order to find if it was a linear function or if it was just a relation or if it was even a function at all in some cases when we were first learning about these. But you might notice over here on the y's, I can't add the same number to each of these like I did with the x's. So we're not going to get an even ratio. For example, I would have a negative 2 here, but then I'd have a negative 6 here, and so on. And negative 2 over 1 does not equal negative 6 over 1. So it is not linear. So I'm going to get rid of those. So then we have to think, can I multiply each of these by the same number? And in this case, we can. If I multiply negative 1 by 3, I get negative 3. If I multiply that negative 3 by 3, I get negative 9. And if I multiply negative 9 by 3, I get negative 27. So because these are all being multiplied, maybe I should use a different color for that. So these are being multiplied, right? And these are being added. That means this is an exponential function. And our explanation could just be that there is a common difference between the x values. That's what this is, the common difference. They all have the same difference. And there is a common ratio between the y values. Alright? For b, we're given a rule instead of a table. The rule we are given for b is that y equals 3x. So the first thing I look for in this case is x an exponent? And it's not. This is just y equals 3 times x, not 3 to the x power. So this is definitely not an exponential function. So if I think about linear functions, y equals mx plus b, this is y equals 3x plus 0. So this is obvious a line. We don't have to show the plus 0, but we can say that this is linear, and our rule could simply be that x, the variable, is not an exponent. Alright, pause the video and go ahead and do Got It 1, A and B. For Got It 1A, you should have gotten linear, and your reason is because the x values have a common difference and the y values have a common ratio. That just simply means you added the same number to get each x, you multiplied by the same number to get each y. And for 1B, you should have gotten that it's exponential, and your reason could simply be because it's in the form y equals a times b to the x. Pause the video and read problem 2 and come back and I will show you how to do that problem. Problem 2 gives us a formula, and whenever we're giving a formula, we just have to think about what we know from our problem that we can plug into the formula. And it says that x represents the number of weeks, and we want to know how many beetles there'll be after 56 days. So since x represents the number of weeks, we have to think about how many weeks are there if there are 56 days. So we just need to divide 56 by 7, right, because there are 7 days a week, and we realize that we're looking at 8 weeks here. So then we just go ahead and say 30 times 2 to the 8th power, and then we can go ahead and calculate that, which this leads to 30 times 2 to the 8th is 256. You are allowed to use your calculators here, and you get 7,680, and then you need to think about your label. If you say weeks or days here, you're not reading the problem correctly. We need to go back to the problem and realize and think about what it is that we were looking for. And when we go back and read the problem, we see it's asking us for how many beetles there will be after 56 days. So this is 7,680 beetles. Pause the video and go ahead and do Got It 2. For Got It 2, you should have gotten 14,580 rabbits. If you didn't, go back and rewatch the example 2 to see if you can figure out where your error might have occurred. And if you cannot find your mistake, make sure to note to ask me about this in class. Problem 3 asks us to graph. It just says, what is the graph of y equals 3 times 2 to the x? So just like in previous problems where we were learning how to graph, we would put our x here, our y here, and then the process in the middle. And we're going to do the same thing here. And then we want to choose easy numbers to work with. So I'm going to go -2, -1, 0, 1, and 2. And by easy, I mean small and graphable. Alright, so if I plug in -2, I end up with 3, let's see if I can do that a little better, 3 times 2 to the -2 power. So we know since it's a negative power, we need to flip it over to make it a positive power. So that's 1 over 2 to the positive 2 power, which is the same thing as 1 over 4. 3 times 1 over 4 is 3/4. So we'll go ahead and put 3/4 over here. And I'm missing a column, aren't I? Here's our coordinate column, the column that tells us what to graph. So the point we would look for here is -2 and then 3/4. Okay? If we plugged in -1, we'd have 3 times 1 over 2 to the positive 1 power. So that's going to be 3/2. So we'd end up with -1 3/2. We know anything to the 0 power is 1, right? And so on. So 3 times 2 to the 1 power is the same thing as 3 times 2, so we end up with 6. And 3 times 2 to the 2nd power is 3 times 4, and that means we end up with 12. Sorry, I wasn't writing these down as I went along. So that would be 2, 12. All right, go ahead and plot these points on your graph. Pause the video. Okay, I'm going to go ahead and do that in red here. So negative 2 means go left 2, and then I'm going to go up 3/4. So about right here. Keep in mind graph paper is a much wiser way to go here. Negative 1 and then 3/2. 3/2 is the same thing as 1 1/2, so that's going about right here. That was a little high. 0, 3 is here. 1, 6 is here, and then 2, 12 is here. Now this is something you'll notice quite often about exponential graphs, is that they go up quite drastically. They're curved and they go up drastically. The thing that's important to notice about this lower section is it's not going to cross the x-axis when it's written like this. There are some cases where if we were to subtract a number over here, we'd cross the x-axis, but those won't come up in this lesson, so don't worry about that. So this part here you want to draw as getting close to the x-axis, but it needs to look like it's never going to cross it. Okay? Alright, go ahead and try got it 3. For got it 3, you should have gotten your first graph would look very similar to the one that I got. Your second graph, notice how it's pointing down? That is because our A value was negative. So please don't think you did anything wrong. It's exactly right. Just when A is negative, things are going to be pointing downward. That's it for this lesson. Go ahead and try lesson check problems 1 through 5. And make sure to be prepared to ask me whatever questions you still have about this when we get back to class together, and we will do an in-class assignment together to practice and perfect these.